Hello everyone. This YouTube video is based on the topic light detection in fiber optics. This is a collective effort by my team members. Our team includes Ishan Sharma, Samyak Parthe, Chinmay Nigudkar and myself Ayush Prabhu. We are being guided by our mentor Mrs. Kadambari Sharma. Light detection in fiber optics is all about detection of light signals through photodiodes, which can be further used for various applications like crack detection on bridges. In this project, we have used a laser light as a primary source of light, which is having a longer wavelength. Photodiode PD638C has been used for light photon conversion into current, and op-amp LF356 has been used for conversion and amplification of current into voltage. These voltage signals would be passed through a comparator which would group and convert it into a digital clock pulse. These clock pulses would be grouped at the specific intervals at the same time and would be sampled. After the conversion, these analog to digital signals would be monitored on a human interface. In our case, it is a handy laptop.
The basic flow of our project is that we will use an optical fiber through which light would be transmitted. This transmitted light would be detected by a photodiode. The photodiode that we have used for our project is PD638C. The output of the photodiode is given to a signal conditioning unit, that is in our case a transimpedance amplifier. The transimpedance amplifier or the TIA circuit is an I to V converter, that is current to voltage converter. Now to build this circuit, we have used LF356 op-amp because it functions at higher frequencies. The output of TIA circuit is given to a comparator IC to generate square wave pulses. The comparator IC that we have used is LM311. Now these pulses are given to counters as input for the counting function. Previously, we had used 74LS193IC for counting, but the circuit was too bulky, so we switched to a microcontroller. Now we are using Node MCU version 3 ESP8266. Now after the counting of pulses is done, we will group multiple pulses together before we input them into the ADC. For grouping of these pulses, we need to use the delay function. So we will be using DS1023 for the delay generation. We are using the serial mode of communication. Now, after the pulse waves are converted into digital format using ADC, we will then monitor them. The ADC part and the monitoring part will be done in the next semester.
So the suggestions given by the reviewers in review 1 was to use Node MCU instead of using Arduino Uno, because Arduino Uno has a faster frequency rate, which is 80 megahertz, compared to Arduino Uno, which has 16 megahertz. We are using the latest version of Node MCU, which is version 3 ESP8266. And another suggestion given by the reviewer was to use the Node MCU ADC, but we are not going to use that because we want to sample multiple pulses at the same given time, which is not possible.
In context of our working model up till now, we have divided the progress in three different parts. In the first part, we have depicted how our op-amp and comparator will be working with different kind of light sources. In the first case, it was using an optical fault detector with alternating light pulses, and in the second case, it was high frequency sine pulse input from a function generator shown by the blue lines. In the second half of our project, we have done the counting part of our code in NodeMCU v3 after upgrading it from Arduino Uno because of its better CPU clock frequency of 80 MHz in comparison with Arduino's 16 MHz. We are still researching on microcontrollers offering better clock frequencies which are also affordable for us as students. In the program tried and tested here, we have counted the number of times when state changes from 0 to 1 to count the number of pulses. And for the second counter, we have grouped the pulses in a specific user defined set. Thus, the higher the clock frequency of the CPU, the lesser the time period it can read, which is very favorable for us if we want to work at higher frequencies. In our third half, we have studied and worked on our programmable delay IC, the DS1023, and tested out parallel as well as serial mode communications in it. In parallel mode communications shown in the picture, we have inputted data using switches as ones or zeros. Following these, our main goals will be to work on integrating optical fibers at the start end of our project and start studying and researching on which uh, IC is most suitable for ADC conversion for our project.